Hi everyone, I'm Matt on Mastomy and I'm back with another video in our series on geodesy. In this video, I'm gonna explain the Earth's motions and why learning them is so important. In one sentence, I can say that understanding these movements is crucial for accurate positioning, navigation, and understanding our planet's shape and orientation, which are the aims of geodesy. So let's dive in. Since various kinds of extraterrestrial measurements play a major role in geodesy, it is necessary to develop some understanding of how the Earth moves among other celestial bodies. Now, I'm going to introduce the four fundamental motions of the Earth in which the Earth undergoes the following kinds of motions simultaneously. The first one is when the Earth moves with our galaxy, which is the Milky Way galaxy, in respect to other galaxies, which this kind of movement can be called galactic movement. This movement occurs on a massive scale and over long periods. The next one is solar system circulation. Within the Milky Way, the Earth circulates around the center of our galaxy along with the rest of the solar system. This motion also spans vast distances and long time frames. It takes approximately 225 to 250 million years to complete. After that, we have annual motion in which the Earth revolves around the Sun with other planets. And this is the motion that we experience as the changing seasons over the course of a year. This revolution is crucial for understanding the Earth's orbit and its variations in solar radiation received. And the last one, but not the least, is diurnal motion, in which the Earth rotates on its axis. And this is the spin that gives us day and night. This rotation affects the planet's shape, causing an equatorial bulge and influences the gravitational field. The first two movements of the Earth are less critical in geodesy because, as I mentioned, they occur on such large scales and over such long periods that their effects on geodetic measurements are negligible. Geodesy primarily focuses on the Earth's shape, orientation, and gravitational field, which are significantly influenced by its rotation around its axis and its revolution around the Sun. These later movements have direct and observable impacts on the Earth's surface, such as the equatorial bulge caused by rotation and seasonal variations due to the Earth's orbit. In contrast, the galaxy scale motions do not produce measurable changes in the parameters that geodesy aims to monitor and understand. One of the most critical movements of the Earth is its annual orbit around the Sun. In a description of annual motion, the dimensions of the Earth and other celestial bodies can be regarded as negligible compared with the dimensions of the solar system. The average distance from the Earth to the Sun is about 93 million miles, while Earth has an average diameter of about 7,926 miles. It means that the diameter of the Earth is less than 0.01% of the average Earth-Sun distance. So, compared to the distance between Earth and the Sun, this is minuscule. As a result, this perspective is crucial for applying Kepler's laws of planetary motion, which describe the orbits of planets around the Sun. Kepler's first law told us that the orbit of any planet is not a perfect circle, but an ellipse, which means that planets move in elliptical orbits in which the Sun is located at one of the two foci. This elliptical shape accounts for the varying distances between the Earth and the Sun throughout the year. In many sources, you can see that the location of the Sun is denoted as H, which is an acronym for Helios, the Greek word for the Sun. According to the second Kepler's law, a planet moves along its orbit with a constant aerial velocity. This law means that planets travel faster when they are closer to the Sun and slower when they are farther from it. But the amount of space covered by the line connecting the planet and the Sun remains constant over equal time periods. As a result, if I want to say this law in one sentence, I can say that in equal time intervals, the area swept by the Earth as it orbits the Sun is always the same. The third law which Kepler introduced is the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This law relates the time a planet takes to orbit the Sun, I mean its period, to the size of its orbit. Specifically, the ratio of the squares of the orbital periods of any two planets is equal to the ratio of the cubes of their average distances from the Sun. For example, if you compare the Earth to another planet like Jupiter, Kepler's third law shows that Jupiter, being farther from the Sun, has a much longer orbital period compared to the Earth. This is because the cube of Jupiter's average distance from the Sun is much larger compared to the Earth's distance. Kepler's third law allows astronomers to predict the orbital characteristics of planets and other celestial bodies based on their distance from the Sun or their orbital periods. Earth's diurnal motion refers to its daily rotation on its axis, which is responsible for the cycle of day and night. Because as the Earth rotates, different parts of the planet are exposed to sunlight, while others are in shadow, creating the cycle of day and night. During this rotation, the Earth rotates around an imaginary line called its axis, which runs from the North Pole to the South Pole. This rotation occurs once approximately every 24 hours. The rotation is from west to east, which is why the sun appears to rise in the east and set in the west. Earth's axial tilt of approximately 23.5 degrees is responsible for the changing seasons by causing varying angles of sunlight throughout the year. Understanding this motion helps us grasp how our planet interacts with sunlight and affects various environmental and observational phenomena. In the simplest dynamic model, the Earth is taken as a rigid body, meaning it maintains its shape and does not deform under the forces acting on it. So it is taken as a rigid body, which, while traveling around the Sun, spins around an axis passing through the body simultaneously. In mechanics, such a body is referred to as a gyroscope. This model assumes Earth spins around an axis while orbiting the Sun, allowing for a more straightforward analysis for its rotational and orbital behavior. This approach helps understand the stability of Earth's rotational axis and the predictable nature of its day and night cycles. Precession is a gravity-induced, slow conical movement of Earth's rotational axis. This is similar to the precession of a spinning top with the axis tracing out a pair of cones joined at their pieces. The term precession typically refers only to this largest part of the motion. Other changes in the alignment of Earth's axis, like nutation and polar motion, are much smaller in magnitude. Precession is primarily caused by gravitational forces exerted on Earth, mainly by the Sun, the Moon, and Jupiter. These gravitational forces create a torque that causes Earth's axis to wobble over time. One complete precession cycle takes approximately 26,000 years. During this cycle, the position of Earth's rotational axis traces out a circular path in the sky, changing the position of the north and south poles. In a general word, over millennia, precession alters the position of the celestial poles and equinoxes. Currently, Polaris is a north star, but in several thousand years, another star will take its place. Precession affects the timing of seasons relative to Earth's orbit. contributing to long-term climate variations such as ice ages. Understanding precision helps us grasp the long-term changes in Earth's orientation and its impact on our planet's climate and astronomical observations. Nutation is a periodic oscillation of Earth's rotational axis superimposed on the precession of the equinoxes. It causes the axis to wobble slightly over time. The angular displacement of the Earth's axis due to nutation is relatively small, with an amplitude of about 9.5 arcseconds. The primary cause of nutation is the gravitational pull of the Moon on Earth's equatorial bulge, which affects the tilt of the Earth's axis. The sun also plays a role, but the effect is less pronounced compared to the moon. Nutation causes slight variations in the orientation of Earth's axis, affecting the position of the celestial poles and the timing of the equinoxes. Nutation occurs on top of the larger precessional motion of Earth's axis. Free nutation refers to the natural, unconstrained oscillation of Earth's rotational axis that occurs in response to initial disturbances independent of external forces like the moon's or sun's gravitational effects. Unlike forced notation, which is driven by external gravitational influences, free notation arises from the Earth's own rotational dynamics, and it includes several components such as Chandler wobble and the related variations. The Chandler wobble is a prominent component of Earth's free notation. It involves a periodic deviation of Earth's rotational axis with an amplitude of about 3 to 15 meters at the Earth's surface. Its period is approximately 433 days, about 14 months. And as I said, it results from the redistribution of Earth's mass and the dynamics of Earth's rotation. It causes minor periodic shifts in the Earth's axis position. These shifts are detectable in long-term astronomical and geophysical measurements. These references were used in this presentation on Earth's motions. For more detailed information, you can refer to these sources. In conclusion, we have explored how Earth moves in space, including its daily rotation, annual orbit around the Sun, and the slow wobble of precession, along with the small periodic changes known as nutation. Understanding these phenomena is not only fascinating but essential for advancing geodesy and improving our global positioning systems. I hope this presentation has deepened your appreciation of Earth's complex behavior and its implications for science and technology. Thank you for your attention, and I welcome any questions or discussions you may have.